Let's begin with a quote from Leonardo da Vinci. "The noblest pleasure is the joy of understanding." What has this got to do with compilers? Compilers cover a broad range of the computer science discipline. Let's take a simple C program. Let's flatten this into a stream of characters, which is what the computer would see. And using an analogy here, let's highlight various parts of this stream of characters. Using regular expressions, we can group these characters into tokens. And we do this in a Lexa source program that is produced using Flex. Having done that, we can group these tokens into coarser constructs or components and assemble them bottom up until you have a single supercomponent. To abuse an analogy here, think of some IKEA furniture that you might assemble. You look at the instruction manual, and depending on that, you assemble various pieces together. Now, Bison is the software we're going to do for that, but the analogy is not perfect because Bison, in fact, produces a machine of sorts, to continue the analogy, such that it will take your stream of characters and assemble it itself, rather than with a screwdriver by hand. So if we had to identify components using this parser, the descriptor, then we might find we have expressions, for example, or statements. And here's what the parser.y looks like. That is fed into Bison and produces a C program that's not too human readable in truth, but it does the job of assembling C structures that represent our program. So what we'll gradually do is hierarchically build up components into coarser components and coarser components still, until we have a single tree with root node. Let's turn this tree the right way up, root at the top. So it's a series of statements. Now, within some of the constructs, we have identifiers or constants, and we need to maintain the state of identifiers and how to address them, and we do this in a symbol table. So this is just a C source code file written by hand. But we need to check also that the semantics of the program are correct. So there would be another phase which does type checking, and it uses a unification algorithm to check that the left-hand side and the right-hand side of each subtree is compatible in some way or another, depending on the operation being performed. And this again is a recursive operation. Having done type checking, we can generate some code, and it's intermediate code, and we will do this corresponding to each of the nodes, or some of the nodes. So in the if condition, we're going to generate some instructions. Inside the if body, we'll generate some more instructions. In the else case, we'll generate some more instructions. And then outside the if statement, we'll generate some more instructions. And then we are going to combine these instructions and hoist them to a higher level, until we have just a single linked list of instructions. And here's the source code. Again, it's recursive. Now, with this linked list, which is just like a C program structures, we can generate or translate these abstract instructions into real assembly instructions for whatever processor we choose. In our case, the MIPS 32 processor. And so we're going to need something like a lookup, resembling a lookup dictionary. And we'll get some architecture-specific instructions. And this is how we do it. We are going to walk through the tree and just do some kind of translation using whatever logic we have in our compiler code. Let's do a demo. We're going to compile these. And then we're going to run the compiler. And it's going to produce MIPS instructions in another browser. This is similar to what's in the slides, but it has a go-to so that we can go back to the beginning and do the same thing over and over again until some condition is false, and then the program terminates. And the source code that gets generated, which you already saw, will look like this. So let's run that in Qt-Spim, a MIPS emulator. Some preamble at the beginning, but we jump and link into our main method address, which is here. And we won't go through this in too much detail, but there's a 99999 here, which corresponds to the source program, and we're going to keep decrementing it. And you see 9998, and then we print that. And we're going to do this again. Well, if we keep going, what we'll see is we jump back and we do the same thing again. So now we see 9997, and we're going to print that as well. And I forgot my new lines in my implementation, but we'll go on without that. And we're just going to keep on doing this over and over and over again. We're going to keep jumping backwards and decrementing. And this is going to take a long time. So a better way to emulate this is to use the command line spim, and we're going to execute spim -f for the input file, our output.s assembly program. But we're also going to capture a timestamp before and after, and then see how long it takes to run to completion. What we'll find is that it takes 3,991 milliseconds, almost 4 seconds. But can we optimize this? Can we get this to run a little bit faster? Can we trim off maybe some instructions that don't have any semantic influence? In fact, if we look at the source code, we'll see that we are loading a 0 constant into a register S2, and then we're comparing S2 against some other value, which is basically comparing whether our variable is 0. This is a bit wasteful because we already have a register that has a constant 0 loaded into it called $0. So can we just delete the instruction that loads a 0 literal into the register? That's what our optimizer code will do. It will iterate over the linked list of instructions backwards, and it will look for loading the constant of value 0, and then instead of referencing this S2 register, it's going to reference the 0 register, and we're going to get rid of the unnecessary instruction. So let's go back and do this now. The only difference, I'm going to do the same thing as before, but I'm going to turn on optimizations. And what we will find is that we are using the $0 register, as we said. And but let's prove this. Let's execute spim again with our timestamps and see what we get. Before we had 3,991 milliseconds. Now we have 3,847 seconds. I ran this a few times, and the kind of statistics I was getting was a 0.2 millisecond speed up, and we are running less instructions. Here's a summary of everything we implemented and some of the analogies along the way and the inputs and outputs. If you'd like these slides, you can scan this QR code and it will give you a link to the online Google Slides.